Welcome. We're looking at Module 4, Task 4, called Are You Rational? It's looking, are you rational? We're talking about rational functions. We're going to look a little deeper. In your own words, define a rational number. Well, it's the ratio of two integers. And then when you look at a rational function, it's also a ratio, but it's a ratio of two polynomials. P of x and q of x are polynomials, okay? And q of x cannot be 0. So, using this, we can do some comparisons between rational numbers and rational functions. Notice over here, we start with 24/30, we factor it, we cancel out, and we end up with simplified form. Same thing here. We can factor it. So minus 3 plus 2. And then divide the numerator. So then we can cancel out here, actually. If you look at this, x minus 3, x plus 2, x plus 2, x minus 2, you notice that x plus 2 is a factor of both the numerator and denominator. So therefore, that divided by itself is 1, and so therefore you've simplified it. But there's something strange that happens here, and that is when you canceled out the x plus 2, you removed the piece of information that said that x could not be negative 2. Because if x was negative 2, then the denominator is 0 and it's undefined. Here's another thing you don't want to do. Why does dividing numerator and denominator the same factor? Because really f of x over f of x, or x over x, or any number divided by itself is always equal to 1, and that's why you can simplify it. But think about this one. You can't do this. Do not do that, because of the x squared minus 1 applies to x, that entire expression. Okay, think of it as in parentheses here. You can't split that up. All right, and it's kind of a distributive property reason for that. So then let's look at an example here. And here we've got x squared minus x minus 6. So we're going to say, I think this was the one we did, isn't it? Yeah. We've got x minus 3 over x minus 2 is how you simplified it. I don't need those parentheses. And that's my f of x. Now, looking at this, x minus 3, x minus 2, you would say, oh, there's a vertical asymptote at x equals 2 because the function is undefined if you're dividing by 0, right? And then you can do a horizontal asymptote because both expressions are the same degree. You take the coefficients, just like we did in the previous one, and the coefficients of the highest degree term, which is x, is 1, so 1 divided by 1 equals 1. So the horizontal asymptote is y equal 1, and you'd think, oh yeah, okay, well that seems all right. However, look at the graph. You can see the horizontal asymptote of 1 and the vertical asymptote at 2, but there's something unusual here where negative 2 is undefined. Okay, I don't know if we're going to be able to see this here, but yeah. But the value of that negative. Here's another way. Maybe we do this here. At x is negative 2, and actually I'll just use the table. So at negative 2 it's actually undefined, and the reason for that, if we go back, is because initially x squared minus 4, if you have negative 2 squared minus 4, you get 0, and that is undefined. So there's what's called a hole in the graph. So it's not readily apparent when you look at the graph, but that is a value that is undefined. So you have to be careful when you are factoring your rational functions that if you eliminate an expression, it's possible that there may be a hole in the graph.